All right, let's get started. So if you look in the content folder, you should see the material we're going to cover today, which is Bodie plots. And depending on where you would have seen them before, hold on, let me make the screen full size. So Bodie plots is really just frequency response analysis. When we talk about it from a controls perspective, because if you have a system that has a frequency output, like one of the things back in the day when I was working on diesel generators, they had a sensor that actually would pick the teeth up on the engine flywheel, and then that would cause a pulse, and then the actual speed of operation was determined by a pulse. So you can use frequency for control. And so when I look at frequency response analysis, we talked about root locus. That's the transient response. I mean, a little bit J omega, but we talked about percent overshoot, and we talked about steady state or 4% settling time. That was more the transient response. And we need a pretty accurate model to go ahead and represent that. We're going to go ahead and do frequency response. So you don't need as precise of a transfer function model, but you can do some experimental, you can try stuff and then see what happens. So we got to do a little bit more on frequency analysis to get a steady state performance. This is the long-term what's going to happen. All right, so let's take a look of a system, and hopefully this stuff doesn't look too unfamiliar to you all. We have a transfer function with G of S, and our value of S is going to be the complex representation of frequency. In this case, it's just going to be J times omega. So we're doing frequency response. So we're not going to add a real component. It's exclusively going to be an imaginary term because that's where our omega term lives. We have a magnitude and an angle because it's a complex number. And we can write that using your calculators like the first one, or you can use Euler's identity. All right. Now, in the time domain, we know that if there's no decaying exponential, it has this form A sine of omega t. That's our magnitude, our angle. So now we're going to change it and not calling it angle. We're going to call it phase, because as things change with frequency, our angle is going to evolve and the amount of phase shift that we're going to experience is going to evolve. So if I have a sine wave that is input as shown, my output here, so this is my input to my block diagram. Here's my output of my system. And this is after about 4 time constants. All the transient stuff. Geez, I can't talk today. Excuse me. Should have had some water. But our steady state output is really going to be a sinusoidal waveform with an amplitude and a phase shift as shown from the transfer function. We're also going to have an amplitude impact because our input is not necessarily a unit sine wave, but has an amplitude as well. The other thing too, this is just kind of interesting, which is you notice the frequency and the input is omega 1. Look at the output. The output frequency is exactly the same. So in circuits, even though we talk about band pass or band reject filters, you cannot get a signal out of a system that has a different input frequency. And what I mean by that is if I put in 50 hertz, I can't get 42 hertz on the output. That's not going to work for an LTI or an RLC system. If you plug in musical notes or something like that, or if you plug in actual music, then what you'll see is that you've got a multitude of frequencies in there, and frequencies will be available on the output. Some of those will not be available to you because they've been filtered out, but the other frequencies that have come in, those will be available. So we're not getting new frequencies, we're just filtering out some of the other ones. So that's essentially what the Bodie plot will do. We also have the magnitude scaling and phase shift. So depending if it's band pass or band reject, that's the concept of magnitude scaling. But we really haven't talked too much about phase shift, other than the concept of an inductor or capacitor, which creates a phase shift with the voltage and or the current. So let's take a look at an RC circuit. Without looking too hard on this, is this a high pass or a low pass filter? Simple RC. High pass or low pass? Or you don't know. It's okay to say I don't know. If you're struggling to analyze this, the way that I analyze this capacitor, what happens to this capacitor at DC? It's going to be fully charged, and all the input voltage is going to pass to the output, right? So at DC, nothing is filtered. At low frequencies, very little is filtered. At high frequency, this capacitor is charging and discharging at a very high rate. So most of the energy for high frequency stuff goes into this capacitor, and very little is going on the output. So this would be a low pass filter. Yep. But let's check that. Let's use Laplace, and remember that in Laplace, the resistor stays a resistor. The capacitor becomes 1 over SC. This is E in of S. This is E out of S. So we can use voltage divider to go ahead and build the system. So my output voltage is, again, the applied voltage, my input, multiplied by the impedance of interest, divided by the sum of the impedances. That's a little bit of a mess, so let's simplify it down. So now we end up with a transfer function that has this block diagram with this gain, 1 over RCS plus 1. We can rewrite that as tau, or our time constant, and then rewrite it so that we have 1 over tau times S plus 1 over tau. This is the equation that we have when we look at e to the minus t over tau. That's the expression that we have. We also know that if you look closely at this block diagram, this is going to have a pole at S equals minus 1 over tau. So now we're going to take a look at that and substitute. So now we're looking at frequency response. We're not looking at any general input. That's what the Laplace domain does. Now we're looking at a frequency input. So anywhere that you see S, you're going to substitute in j omega. So the S term that we had here, or we could just do it over here, RC times S plus 1 becomes 1 plus JRC omega. This is a big difference for me for Bode plots. Remember how most of the time we want our denominator to have an S that's just multiplied by 1? In Bode plots, you always want the 1 to be by itself. So if you had, I don't know, let's say you had S plus 7, you would rewrite that to be S over 7 plus 1. Okay? And then you're going to have to factor out the 7 over here, but you always want it to be a plus 1. So this is a big difference in the way that we've analyzed stuff before. We just want to make sure that we understand that that is our approach. So now let's do the math. Magnitude and angle. This has a magnitude, right? So let's look at 1 over 1 plus j RC omega. This is going to be 1 at an angle of 0. This is going to have the magnitude of the square root of 1 plus the imaginary part squared. That's square rooted, right? Because that's the Pythagorean theorem. I didn't include the square over there, but 1 squared is equal to 1. Then the angle over here. What's the angle that I'm going to get over here? $90 or 180? Well, keep in mind the real part is equal to 1. The imaginary part is equal to omega. So the angle I'm getting here, what does Sakatoa say? Opposite over the hypotenuse is the sine, but I don't know the hypotenuse yet. What do I know? I know the opposite over the adjacent. So what should I put in there to get the angle? Sakator, sine is opposite over the hypotenuse. Tangent, very good. So the inverse tangent of the imaginary part over the real part is the angle. If you remember when we did our root locus stuff, we get the magnitudes by multiplying or dividing the magnitudes. And we get the angles by adding or subtracting the angles. That's what this is over here. Okay. Everybody understand that? Does that make sense? Because we do this in Bode plots a lot. We really rely on the concepts of using complex numbers to be able to get that result for us. Now I'm gonna have to erase some stuff, but that's okay. So let's let our value of R times C equal 1. So let me erase a little bit of stuff because I'm really gonna trip on myself. So with my value of RC equal -1, I'm gonna have a pole at -1. And now my equation just simplifies to 1 over the square root of 1 plus omega squared and the inverse tangent of omega because the RC is just equal to 1. So then I can write this using Euler's identity. Again, it's the same thing. Let me erase a little more. Okay, so now what's happening graphically is I have my R times C value is going to be equal to 1. So now all I'm left with is omega, and I'm left with 1. So exactly what we did when we did our trying to figure out the angle, we have that value here. Now, here's the thing that's interesting. Remember, omega, this is a variable of omega. So omega can either go up or down in frequency, can it? So as I go up in frequency, what ends up happening to the magnitude of the impedance, if you will? Maybe impedance is not the right term. What ends up happening to this term right here? Yep. It's going to increase its magnitude, right? And remember, since this is in the denominator here, right? When I multiply my input by this term over here, that term gets bigger and bigger and bigger, which means I'm going to get less and less on the output. So when we talked about this being a low pass filter, you can see as I increase this, this magnitude increases. When I go down, when I get all the way to DC, I'm just getting the input. The gain is equal to 1. So graphically, what I'm trying to do is just show you how as I increase or decrease the omega, it has the effect of increasing or decreasing that magnitude. Now, can you see it over here? You see this as a low pass filter? Look at DC, my frequency of 0. What is the gain of the system? At DC. It's 1. Has that attenuated the signal at all? Not at all. The input is 1, and that means, all the input goes to the gain, it's going to be equal to 1. So there's no attenuation, magnitude attenuation. Input's equal to the output at DC. Same thing over here. Look at the frequency. What do you know about the frequency? No phase shift. At DC, there's no phase shift. So this shows at DC, we have a pretty good low pass filter. What happens as we start increasing the frequency? Our gain, which again, you multiply the input by the gain to get the output, the gain starts dropping. Goes down and down and down until it reaches a pretty low value, which is about 5 radians per second. Same thing over here. We get a phase shift. And do you remember in capacitors, what type of a phase shift we would expect for a system? One capacitor? Get a 90-degree phase shift, yeah. So if you were to allow this frequency to increase over time, you would eventually get to 90 degrees. That's essentially what happens is it gets to 90 degrees at infinity. We don't have that, but we in electric circuits assume it's going to give us a 90-degree phase shift. So you can see, hopefully pretty well with this example, that for an RC, this is called a passive filter, right? We don't have any energy into it. So a passive first order filter, we basically can get this type of characteristic. All right. And it works really well. We've had these for many, many years. It does a reasonably good job. We're going to learn more about the slope of the gain over here, as well as the slope over here, to make it so that we can sketch these pretty quickly. So one thing we need to do is we have to plot in logarithmic scale, because this one doesn't really give us nice straight lines, correct? We get some pretty goofy lines. So our magnitude plots are going to be logarithmic. Our angle plots are going to be semi-logarithmic, and we'll see where that comes from. So why do we do logarithmic? Well, remember when we had this over here? So this is just a system with one pole, 2 poles, and 1 0. So we would have a magnitude and an angle up here, and a magnitude and an angle over here, and a magnitude and an angle over here. So if we wanted to calculate this, we would have to divide these, and then we'd have to subtract the angles, right? So this one's a little more work because we have to multiply or divide. Wouldn't it be better if there was some way of converting these magnitudes so that they were being added or subtracted? Do you remember dB? What is a decibel? Deci, okay, for anybody who's into it's physics, or even if you're looking at System International for units, what is deci used for? It's 10, right? So a decibel is 20 log 10 of something. The reason why we have the 20 over here is because this is a voltage. This is for power. So a decibel is using it for power. But if you remember, P equals V squared over R. So we take P, if we want to do it in decibels, I should say. So we do 10 log 10 of V squared over R is going to be equal to 20 log 10 of my V over R, right? That's when you get that value. So where does a 20 come from? It actually isn't from the definition of a decibel. A decibel is a power measurement. It's just that we get the 20 for voltages and current using that value. So if we use 20 log 10 over here, so instead of doing this one, we do 20 log 10 of, of our G, I'll just call it G of S. What we're going to do now is when we have the 20 log 10, we're going to add or subtract our magnitudes. So with Bode plots, we use the gain in dB. So that's where we get the log. And for our phase shift, we use theta in degrees. So when you do Bode plot analysis, it's always going to be a magnitude plot, which is going to be a dB plot. So we have to convert that to dB. And for our phase shift, we're going to go ahead and do the same thing. Now, here's the other thing that's interesting. When you look at a Bode plot, this is log scale. This is standard scale. And the reason why this is standard scale is I've already converted this into logarithmic scale by taking 20 log 10 here. So I don't put this under a log scale. I just put it under standard scale.
So even though this says it's log log, I'm being a little sneaky because I've taken the log already to get the decibel value. So it's displaying the log, but I got to take the 20 log 10 of it. Phase shift, it uses the standard phase shift. So if you were going to look at semi-log paper, see if I can bring that up. Get this out of the way, come on. Can you see? Probably hard to see, but log paper would tell you that to go from 20 to 40 would take less time than going from 0 to 20, right? If it was log scale. But you can see each of these is exactly the same. To go from 1 to 10, it should be essentially the same length, but because you can see this is log scale, I go from 10 to 100 in the same distance that it goes from 1 to 10. So this is the semi-log paper that you use for Bode plots. This is the standard axis, and this is the logarithmic axis or log scale axis. All right, so that's important to understand how we use logarithmic paper. And the only reason we use, I don't know why my throat's really bothering me today. Apologize for all the clearing of the throat. The only reason why we use we say it's logarithmic is because that is done in dB. But now take a look, instead of multiplying and dividing, then I can go ahead and add or subtract any of those terms. So I'm going to convert my Bode plot, not my Bode plot, my transfer function. I'm going to convert it to dB, which means I just take the magnitudes and divide it over here. You'll notice this is already set up in standard form, which you'll see that this omega, which is my input variable, and that omega 1, omega 3, omega 2 is the pole or zero associated with that. That's very important because that defines what we call our break frequency. Let me make some room over here. I'm writing all over these things because it really is kind of interesting to see Bode plots. It gets me excited about it because it really is a cool idea, concept for Bode plot analysis. Okay, so as I mentioned, your omegas, the poles or zeros, will end up becoming your break frequencies. Now, does anybody remember a break frequency? See if we can bring that up. What's the definition of a break frequency? Breakaway point? It isn't the same. Nope. That's for root locus. That actually has nothing, it doesn't necessarily have anything to do with frequency. And in fact, it doesn't because it's on the real axis where there is no frequency associated with it. Maybe, possibly. Remember our circuit here? How did we define the break frequency of that?
It's like the frequency at which
Resonance happens? Not necessarily. If you look at the definition of break frequency, it's the half power frequency. Which means half the power goes down here and the other half goes straight through. So the frequency, you can determine that because if you remembered my 1/1 plus RC omega, that term squared, when will you have half the power? When that equals 1, right? Because then you're left up with 1/2. Well, 1 over the square root of 2. But then when you square it for power, you get 1/2 the power. So your break frequency is an actual definition for the half power frequency. And we'll see how that comes into account more and more. So when we do dB, we're going to add our poles and zeros, and we're just going to add or subtract the magnitude, the log magnitude. We don't have to do any multiplying or dividing. It's exactly the same as the phase shift. So it makes the math a little bit easier. Jeez. Let me get this out of the way. All right. So let's take a look at a very simple one, a single pole or zero. And it doesn't matter if it's a pole or zero. We'll look at it just this way. So we have 1 over S divided by any break frequency we want. And we want to evaluate so that our omega can vary between 0 hertz to whatever frequency we want it to vary. So omega here is a variable that's allowed to change. So when we're doing Bode plots, our term is going to be 1 over J times omega over omega sub 1. All right, so let's go ahead and convert the magnitude into dB. So we're going to do 20 log 10 of 1 plus J omega over omega sub 1. I need to get the magnitude of that. So we've got the magnitude term here. And we end up with this expression over here. Now, at our break frequency, when omega equals omega sub 1, we have 20 log 10 of the square root of 2. And that equates to 3 dB. So another term for our half power term frequency or break frequency is the 3 dB point. So when the output is 3 dB above or below the input, that's when we have our 3 dB. So we will use this a lot because it really helps define what our plots are going to look like. Now, anybody know what the term octave is? How about my musician friends? What's an octave? A set of 7 notes?
7 major home, natural home.
If I remember right, an octave is a series of 8 notes.
Series of 8 notes? I'm not a musical person, so I don't know either one. But if I tell you, okay, who can sing? Or play an instrument? So if you're playing an instrument and I say play it 1 octave higher or 1 octave lower, that's not a note, right?
So you may play the same note, so when you go down, it sounds like more like that.
Yep.
Then as you go up, sounds like more like here, like the same.
Yes, it's the same note, but it's an octave higher or lower. An octave means you've doubled the frequency. So 1 octave higher means you've gone from 10 hertz to 20 hertz. 1 octave higher from 20 hertz is 20 hertz is 40 hertz. I almost tricked you. Yes. You double the frequency every time. So you don't double it and go 10, 20, 30. You go 10, 20, 40, 80, on and on and on. So for our band member folks in here, you talk about octaves as a doubling of the frequency. What about a decade? Let's see if we know that term. What's a decade? I don't know if that's a musical term, but if you think about, and so my wife tells me this all the time, understanding music is just understanding math because the notes all have a specific frequency and all the bars, you go up or down. It's supposed to be a mathematical equation. So octaves, they use it all the time. Decades, I'm not sure if they use it all the time. How about any of my musician friends? Is there a doubling? Is there an equivalency for doubling? How about Jake? I don't see Owen in here. Do you talk about decades? That's exactly right. 1 decade is a frequency that is 10 times higher. So if I go from 10 hertz and I go 1 decade above, I go to 100 hertz. 1 decade above 100 hertz is 1,000 hertz. So we use octaves and decades a lot in our Bode plots because we're trying to look and see what happens when the frequency doubles or goes up by a factor of 10 or 50 or 100. So we'll talk about that here. All right, so a couple other things. Now, we're going to look at our break frequencies, but we're going to kind of get cute about looking at our break frequencies. And we're going to look at our frequencies that are much, much further away from our break frequencies than we think. So let's look at the first case when our actual frequency we're trying to assess the response is much, much lower than our break frequency. Let's say it's a decade away, 1/10. So if we do a decade over here, and we'll plug in the number, 20 log 10, what's a decade below? Or multiplied by 0.1? So 0.1 times omega I over omega I squared, which is equal to 20 log 10 of 1 plus 0.1 squared, which is 20 log 10 of 1 plus 0.01, right? Would you say 1 plus 0.01? Could we call that 1? 100th is pretty small, isn't it? So for 1 decade in frequency, which we consider that to be a much lower frequency, we're only 0.01 off. So the concept that we're using over here is if we're about a decade away, then we're going to say for our break frequency, if we're 1 decade away from our break frequency, there's nothing, there's no contribution here. So our 20 log 10 for this particular pole or 0 is going to be 0. If we're much greater than that, okay, so we already talked about the fact when they're the same, we talked about 3 dB. If we're much greater, so 20 log 10, and let's do a decade above, 1 plus 10 squared. Would you say 100 is a lot bigger than 1? Kind of. Let's take a look. Let's go to MATLAB. And let's do the square root of 101. 10.05. And we all know the square root of 100 is 10. So you're only off by 0.05 in this application. So I wonder if I'm way less than about a 1/10 of a way, or a 1/10 of the frequency, then I'm going to say that that contributes 0. And if I'm a factor of 10 higher than my break frequency, then I'm going to say that I'm getting a lot of contribution. And then at my break frequency, it's going to be the 3 dB point. So, the last thing I got to mention is the concept of a decade. So for every factor of 10, right, because we said that this is close enough to say 20 log 10 of 100. Square root of 100 is 20 log 10 of 10. But if we go 20 log 10 of, let's see, so that's going to be 100 squared. There's a difference of 20 in between there. So for every decade frequency increase, every multiple of 10, we're going to say that the slope of our gain is going to go up or down by 20 dB per decade, okay? And the reason why we say up or down is because we could have poles or we could have zeros. So here's our approximation for our plot. So we're gonna say that for values much, much less than our value, our break frequency, we're not gonna contribute anything. And we're gonna approximate it by saying all the way till we get to our break frequency, it's gonna be 0. Then when we hit our break frequency, we start to see that the gain of the system is gonna go up or down by 20 dB per decade. Right? And that's going to continue to go on forever. It's either going to go up or down forever. As long as we increase frequency, it's going to go up or down forever. This is an approximation. Does everybody know where the worst case error is going to be? When do you expect that you're going to have the worst case error between the exact and the approximation? Right here. And we've already said that that's 3 dB difference. So the worst error you're going to get in your Bode plot is going to be 3 dB maximum. And it's always going to be at the break frequency. So when you're doing senior design projects and you're designing a filter or something like that, what do we tell you to stay well away from? The break frequency. Because the break frequency means you still can get a fair amount of stuff passing through or being rejected that you don't necessarily want. So if you're staying well away from your break frequency, maybe a 10 or 10 times that, you're going to be pretty accurate. You're going to be pretty close. We already saw that when we did this one, we had 10.05 instead of 10. That was pretty close. If you want to do this one, let's just do this one over here, the 1.01. So we take the square root of 1.01. Isn't that pretty close to 1? So you can see there's hardly any error. And if I took 20 log 10, and it's going to be, is it log 10? I think it's log 10 because if I just do regular log, I think it's log E. So you can see that that's pretty darn close to 0, right? 0.04. Where if we know if we do, let me just double check to make sure this is right. So you can see it's 0 versus 0.04. So pretty small numbers there. So this is our approximation. And this is how we do Bode plots. We don't want to do exact Bode plots. We want to do approximations because if we have semi-logarithmic paper, we can draw these really accurately. So let me show you the exact one. I kind of sketched it in. So you can see, hopefully you can see that that's the error that we're getting. It's a maximum of 3 dB at the break frequency. Okay, so if we plot versus we do our approximation, here's our frequency response. So this is kind of zoomed in, and you can do 20 log 10, and this is a log of relative. So you can see that this is written generically for any break frequency. This is for what we would call a 0. This is a 0, and we'll talk. Hopefully, we have enough time to talk about that. But if we're log 10, 0.1 minus 1 over here, which means we're 10, then you can see we're almost perfect. If we're up here at a factor of 10, right? So log 10 to the 1, we would be 10 times. We're pretty good. You can see outside this region right here, whoops. This region right here, we get our approximation is pretty darn close to the exact. And even some could argue that even when you start moving closer, it's pretty darn close to it. But we'll just assume as long as we stay away from those break frequencies, we're pretty good. All right, so now let's look at how we add these terms in. The first one we'll do is, let's look at a positive gain of K. So this is not a pole or a 0. This is we're taking our G of S and multiplying it by K. So the question is, what does this do to the magnitude in the phase? Well, remember, K is a real number. So if I multiply something by a real number, whoops, that's going to be K at an angle of 0, right? Exactly right. So I do 20 log 10 of K. That's our magnitude. And our phase shift is 0 because there's no J term that I'm including there. It's just a complex number. So for the phase shift, every time we introduce a gain, we do nothing to the phase shift. But the magnitude, we can either increase it or we can decrease it. So if K is equal to 100, right? So let's do it this way. K is equal to 100, so we're going to do 20 times log 10 of K. That's equal to 40. That's 40. We're going to add 40 dB to whatever our system is. So if you want your system to be stronger, you're going to multiply that value by 40. How would I decrease that, the amplitude? How do I make it go less? Yeah, like if I put something that's 100, so I multiply the block diagram by a value of 100, that's my value of K. How do I make it less? Divide? Kind of. You don't divide, you multiply by a number less than 1, right? Dividing by 10 is the same thing as dividing by or multiplying by 0.1. So if I did my value of K equal to 1 divided by 100, now I do this over again. What do you think is going to happen? It's going to decrease it a lot. It's going to decrease it by 40 dB. Right? Now you really can see it. So multiplying it by 0.1 or 0.01 has the same effect of multiplying it by 100. You're just going to decrease the attenuation by a factor of 40. So anytime you multiply something by K, you can either increase it or you can decrease it. So going back over here, here's our magnitude plot. It's 20 log 10 of K. We just did that. Our phase plot is 0. And you can see that our magnitude is going to be above 0 and it's going to be fixed. No matter what the frequency is, I can go 0.01 hertz or radians per second. I can go up to 1,000,000. And regardless of the input frequency, that gain is a constant value. It never deviates. Same thing with a phase shift. The phase shift never goes up or down. It doesn't depend on the value of omega. So it's the value of K, again, because K is a real number, it has a constant gain adding or subtracting, depending if it's less than or greater than 1. And then its phase shift is always going to be a 0. K, and we've done this a lot in this class, must be greater than 0. You can't have a negative K. It has to be a positive number. All right, so here is not much to report, right? You can see if my gain is 4, it's way up over here. And if it's a quarter, it's way down over here. Those are the two magnitudes. One's way up over here. One's way down over here. This is the phase shift is 0. All right, so now let's go ahead and add a pole at the origin. What is a pole at the origin equal to? One over S. Isn't that an integrator? So what do you think that's going to do to the gain? This one's not intuitive. It's going to increase right off the bat, right? So as my frequency starts, it's going to go up or is it going to go down? That's the 0. That's the pole. It goes down. Because remember, it's in the denominator, right? 1 over S becomes 1 over j omega. When I do the gain of that, that's going to be equal to 1 over the square root of 0 squared plus omega squared. which is 1 over omega. And that's going to be 1. So it's 20 log 10 of 1 minus 20 log 10 of omega. So it goes down at 20 dB per decade. So when we think we're adding an integrator, it's a great idea. Is it? Well, think about for frequency. At DC, it does exactly what we expect it to do, right? It has a really high gain. It's going to keep integrating on. But as my frequency increases, that integrator is having a harder and harder time keeping up with that. Opposite for a derivative, right? It doesn't change at DC, so it does 0 at DC. But the faster it changes, the more the derivative has an impact. So my derivative here, faster rates of change means a bigger contribution. My integrator is the exact opposite. And you can see when I multiply by S, I get a positive 90-degree phase shift. When I integrate 1 over S, I get a negative 90-degree phase shift. Okay? And those are the values that we end up with there. How about a non-zero pole or 0? So at this point, we have a break frequency. So if my break frequency is here, now I have to use those rules about 1/10 starts at 0 until I get to my break frequency. I do nothing on my break frequency until I get to it. And then I will go up if it's a 0, or I will go down at 20 dB per decade indefinitely. So let's take a look at our plot. There's our 0. There's our pole. Now, how about my phase shift? This one's harder. How about my phase shift? It's based on the same principle. So we have this over here. So we have 1 plus omega over the break frequency squared, square rooted. So that means we have 1, and we have, let's see, omega over omega sub 1 over here, or omega sub I. And here's theta. Now this one we are looking at the tangent, right? So at the break frequency, at omega equals omega sub I, what is the inverse tangent of omega over omega sub I equal to? Well, what's the actual equation? If these two are the same, what's the inverse tangent of 1? (45 degrees). What's the inverse tangent? So if we're 1/10, it's approximately 6 degrees. What's the inverse tangent of 10? I think it's 84 or 85 degrees. What's the inverse tangent of 0? 0. Inverse tangent of infinity is 90. So for each pole or 0, this is what's very different about Bode plots for phase. Because for our magnitude plots, our magnitude went up or down at 20 dB per decade. Over in our phase plots, they will go up or down at 45 degrees per decade, right? Because you can see that we'll call that close enough to 0. We'll call that close enough to 90. So it doesn't go up 90 degrees, or doesn't go up or down 90 degrees per decade. It goes up or down 45 degrees per decade, and it stops at 0 and at 90 or minus 90. So let's take a look. Let me erase this out of here so we can actually see the plots. So here's our value. It's equal to 0. We said it's about 6 degrees. So we'll say that's close enough to 1 because we're doing approximation. Over here, it's 45 degrees. When it's a 10th, 84 degrees, we'll call that close enough to 90. When it's much, much greater, we say it's 90. So at 1/10 the break frequency, because it's 45 degrees per decade, we start adding or subtracting a phase shift. And the phase shift is 45 degrees per decade. We got to get to 90. So if we started at a 10th, and this is 45 degrees per decade, don't we have to stop after 2 decades? Yeah, because we hit 90. If it takes us 1 decade to get to 45, we need another decade to get to 90. So where the phase shift is quite a bit different for our Bode plots, it stops at a value. It doesn't continue to take away phase shift. There is one element that does take away phase shift. That's if it has a system delay, but we probably won't get into that this semester. So here's one where you have it in the denominator. So this is a pole and it goes down, same thing. So this shows you for poles and zeros, magnitude plot. We know about the plus or minus 3 dB per decade. For the phase plots, this is where it's a little bit different. It actually crosses exactly at the break frequency. So the approximate or the exact, they give the same number at the break frequency. The worst case error is right here and right here. 1/10 above and 1/10 below. This is off by plus or minus 6 degrees on both sides. Okay. All right, let's do one quick example and then I'll let you go because everybody's brain must be hurting, right? This is a lot of math but it just gives you a little taste of doing Bode plot and frequency response. So let's take a look at a simple block diagram that has a transfer function of 100 or 1,000 times s plus 3 over s times s plus 12 times s plus 50. The very first thing you need to do is set it up in standard form, which means I have to divide this by the break frequency, this by the break frequency, and this by its break frequency, because I want to have it set up in standard form. When I do that, that 1,000 becomes 5. So now I have a K of 5, which is going to affect the magnitude 20 log 10. Then I'm going to have another one here. That's not going to, so let's do that. So 20 log 10 of 5, what is that going to be equal to? So 13.98. So my value of K is here. So that's going to give me a straight line for my magnitude. This one over here, the S plus 3, this one way down over here, that's a 0. So it does nothing until I hit the break frequency, which is here. Then that goes up. This one does nothing until it reaches 12. So I run along until I hit 12 and then it goes down. No, 12 is, sorry, shorter than that. That goes to 10 and then let's say 12 is about over here and then it drops off. And then the next one is 50, 20, 30, 40, 50, and then goes down that way. So then we add these all together. So let's see if I can change the color. Let's change it to green. So I'm going to go like this. I'm going to be flat, 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 flat until I hit here. Then I'm going to go up at 20 dB per decade until my next pole comes into play. Then it's going to flatten out because I have one going up at 20 and the other one going down at 20. So they cancel each other. And then I'm going to continue until I hit 50. And then I'm going to start going down. So this looks to me like it's a band pass filter because over here, I've got a lot of gain over here. I'm also doing a little bit of low pass filtering, but I'm really getting a lot of response when I look at there. And then the nice thing is I can calculate approximately what this is going to be, because this is at 14 all the way until we get to 3. Right? So from 3 to 6 is a doubling of frequency. So let's see. So this is 1, 2, 3. Oops, wait a minute. Oh, I should have started earlier. Sorry. Let me fix that one. I should have started a little bit earlier. So 3 is over. Let me do it over here, because I'm getting lost in my numbers. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 20, 30, 40, 50. So I'm about 14 until I hit 3. Then I'm going to go up at 20 dB per decade until I hit 12. Then I'm going to flatten until I hit 50. 20, 30, 40, 50. Then I'm going to go down. So right over here, this is 14. At this point, I've gone up 3 dB. So at this point right over here, this should be 17. If I double the frequency, I get to 12. So right here is when I hit 20 dB. And obviously I'm not drawn to scale, but you get the idea. So I went from 14 to 17 to 20. I flatten out, and then I start to go down. That's how you do the calculations here. Oh, I forgot about the S, darn it. Well, I forgot about the S, so I screwed that one up. So I didn't have the S term in here. So the S actually starts dropping right off. So let me, I'm gonna erase this one because I forgot the S term. Actually, you know what? Let's just pretend the first one, we didn't actually include that one in there. So the first one was the one that we drew. And then this one will be the second example, where we have one going down immediately at 20 dB per decade. We have our other two. You can see the colored lines. One's at 12 and one's at 50. Here's the 0 at S equals 3. That's minus 20 dB per decade. And the only reason why it moved up over here is because this is 20 log 10 of 5. That's why it's moved up. So that's that constant value over here. And then I continue on. And that's the value. This final one over here goes down at 40 dB per decade. Okay. Let's do the phase shift, and then we'll stop here. So remember, this one has no angle. This is an integrator. So this does a 90-degree phase shift right off. This does 0. This does 45 degrees positive. This does minus 45 degrees and minus 45 degrees. This is per decade. So we're going to start off here at minus 90. So this is minus 90. Now we're going to add in the 0 at S equals 12. So we're going to start that at 1.2. So this is 1.2, not 12. And it ends at 120, because that's 1 decade above and 1 decade below. I do the same thing for the pole at 50. So we started at 5 and go all the way to 500. And then we're going to do the 0 over here. So this starts at 0.3 and ends at 30. And then we add them together. And notice, so in the previous one, it just kept going down at 40 dB per decade. This one stops, and it stops at minus 180. Why does it stop at minus 180? Because I have 1 0 and 3 poles. The difference between there is 2 at minus 90 degrees. So you can always tell where you need to stop by looking at the number of phase shifts or number of poles and zeros that we have. Now, this is if you did it exactly in MATLAB. So if you did it exactly, this is what you get. But by drawing it kind of roughly, we get a pretty close approximation for both magnitude and phase. That's the magnitude. That's the phase. And that's how we compare doing the exact approach. You can always do the exact approach. You just plug in a value of j omega over here, and then you do the magnitude and gain calculations. That's how MATLAB does it. You can just do it automatically. Okay. Questions? People are like, yeah, this is confusing stuff, but it is a little bit, but it's a lot of it, just the math, and it follows along from our transfer function approach. All right, questions. Oh, somebody has a question here. 10 times the fundamental. Yep, very good. But this, hopefully, if you took circuit analysis with John Allen, if you took 342, when he did his frequency response stuff, you know, you basically were doing the approximations. You just didn't realize you were doing the approximations, but that's all we did. We look at the break frequency and we start above and below. But this is the mathematical sort of definition behind it. All right, well, that's all I had for today. So come on Thursday with any questions you have about the final. We'll do a semester in review. We'll give you some tips to study for the final exam. But that's it. I'll just put this up here so people have it. Here. What's that? I'm not going to type one out because we really don't have any new material. So it's the same as the first 3 exams, but we'll just go over, you know, we'll just look at those individually. And then we'll just see if people have specific questions. Those are really detailed. So that's probably why we don't need an additional one. All right. Well, that's all I had. Have a great day, everyone. We'll see you on Thursday. Take care. Thank you.